Hey guys, tonight, we drift far beyond our cozy little solar system, past the dust of Mars, past Neptune's icy breath, past the endless halo of the Oort cloud, into a region so ancient, so dense with stardust and radiation, that you can almost taste the metal in your teeth. If you enjoy these deep space journeys and cosmic stories, don't forget to hit that like button and subscribe so you won't miss the next time we travel across time and starlight together. We're going to follow the life of a very special star, one that, against all odds, absolutely refuses to die. It's like the cosmic equivalent of your grandma who's outlived two husbands, a war, and the entire VHS industry. You're a million years old now, maybe two. And while that would be enough time for a species like ours to crawl out of caves and start arguing about taxes for a star like you, it's just Tuesday. You don't age, you flare, your surface blisters with heat, 30,000 Kelvin and rising. The ultraviolet radiation you hurl into space would bleach the bones of anything foolish enough to orbit you without shielding. No sunscreen in the known universe is SPF, don't evaporate sadly, and your stellar wind's a hurricane of particles strong enough to strip the atmospheres off baby planets like peeling fruit. Still, you're elegant in your fury. A ballet dancer made of plasma. You fuse helium into carbon now, and deep within your core, heavier elements begin stacking up like a game of nuclear Jenga. Oxygen, neon, magnesium. All these tiny firestorms, nested like Russian dolls. You are what physicists call an onion star, a terrifyingly appropriate name, because if someone peeled you open, they'd cry probably from being vaporized, but still. Here's your mainstream historical tidbit for the night. Betelgeuse, the massive red star in Orion's shoulder, is believed to be in the late stages of this same life cycle. It's swollen, unstable, and potentially ready to blow at any cosmic moment. Stargazers hold their breath every few years, wondering if it'll go supernova in our lifetime. Spoiler, it hasn't yet. But maybe tonight, keep an eye out. Just not directly. You like your retinas. Inside you, the pressure is unbearable. Your core contracts harder, tighter, smaller. Temperatures rise to billions of degrees. You're forging iron now, the end of the line in stellar alchemy. Iron is your last act. It takes in more energy than it gives back. And when your core fills with it, fusion just stops. Now remember that toddler with the finger paints from earlier. Imagine they just spilled paint thinner on an open flame. The pressure drops. Gravity no longer held in check by fusion winds. In less than a second, your core collapses. The atoms themselves are crushed. Electrons and protons slam together to make neutrons. That's right, entire atoms reduced to their subatomic bits. It's like folding a skyscraper into a shoebox, then stepping on it. Boom! This is a supernova. You are now the centerpiece of the most violent event in the universe, besides the birth of the universe itself. Light rips through the nebula you once called home. Your outer layers are blasted into space at 30,000 kilometers per second, fast enough to circle Earth in under 2 seconds. The energy released in this moment is so immense that for a few weeks, you outshine your entire galaxy. Not bad for a dead star. Now, here's a little-known fringe fact for you. Some scientists believe supernovae might have helped shape human evolution. Radiation bursts from nearby stellar explosions could have subtly altered Earth's climate, affecting our ancestors' migration patterns, survival instincts, maybe even sparking higher intelligence. So yes, next time you're stuck in traffic, you might be able to blame an exploding star from 2 million years ago. Historians still argue whether early Chinese and Arab astronomers recorded supernovae long before Western science caught on. The guest stars mentioned in ancient scrolls may well have been stars like you, dying with flare lighting up night skies and then fading before anyone could quite explain what they'd seen. But your story doesn't end here. No, no, you're not some firework that explodes and fizzles. Because inside that supernova, something remains. It's tiny, it's dense, it's angry. It's you, condensed now into a neutron star about 20 kilometers across, but still heavier than our sun. Imagine taking Mount Everest, compressing it into a teaspoon, and realizing that teaspoon still weighs more than your car. That's what you are now. You no longer shine in the traditional sense. No more warm golden rays or lazy sunbeams. You're cold, hard, fast. Your surface is a crust of iron atoms packed so tight they barely know where one ends and the other begins. And underneath that, a soup of neutrons so dense, it laughs at our silly concept of solid. You're spinning, fast. At birth, most neutron stars rotate dozens, sometimes hundreds of times per second. You're essentially a cosmic Beyblade on an existential mission. And something else happens. You start to beam. Twin jets of radiation shoot out from your poles. If Earth happens to lie in the path of those beams, humans will pick you up as rhythmic pulses blinking in perfect time. The world will name you a pulsar. You're a lighthouse in the dark, a reminder that even in death a star can find rhythm. But while they stare up and listen for your ticking heart, they have no idea what's coming next. You were supposed to fade. That's the usual deal, isn't it? Burn bright, explode, then vanish like a dramatic diva who knocks over a mic stand and storms off stage. But no, not you. You stick around, compact, brooding, humming to yourself in the dark. And now something new is happening. Inside that crust, harder than diamond, smoother than ice, there's a restlessness, a tension. You've been spinning fast since the moment of collapse, like a figure skater pulling in their arms mid-twirl. But even neutron stars get tired. You begin to slow, just a smidge. Every once in a while you skip a beat, not figuratively, literally. Scientists call it a glitch. You, the once perfect cosmic metronome, suddenly hiccup. Your spin stutters, then it resumes slightly offbeat. Not enough to notice on a casual stroll through the galaxy, but just enough for those paying attention. And oh, humans are paying attention. Let's back up for a second with a bit of real-world history. The first pulsar ever discovered in 1967 was so regular in its timing that astronomers actually thought it might be aliens. They named it LGM-1 for Little Green Men. No joke. It pulsed every 1.3 seconds, click, 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 so precisely that it embarrassed the atomic clocks of the day. But stars don't just glitch without a reason. You're shedding energy. And as your outer crust relaxes just slightly, it cracks. A starquake. That's right. Not an earthquake. A starquake. Plates of superdense matter shift, and the release of stress causes your spin to stutter. Imagine a planet-sized bell with a hairline fracture, still ringing, but wobbling now and then, just enough to remind you it's tired. Then come the wobbles. You no longer spin like a ballerina on a smooth floor. You precess think of a spinning top, slowing down its axis, tracing a lazy circle. The jets of radiation you've been shooting out, they shift. Sometimes Earth isn't even in the path anymore, and for days, months, even astronomers think you've gone silent. But you haven't. You're just off angle. One night you reappear. Your pulse is back, and everyone stares, wondering what just happened. The fringe crowd starts whispering. Again, what if these stars are trying to communicate? What if the pauses, the glitches, the bursts there, Morse code, on a galactic scale? Historians still argue whether ancient monuments aligned with stars were built purely for beauty or for messages. Some even think these monuments were receivers-coded temples designed to echo back to the sky. Maybe your stutter isn't a malfunction. Maybe it's a pattern. You're evolving, and now, oh boy, you start to do something nobody expected. Your beam changes, not just direction or strength, it morphs. Like you're playing with the tuning knobs on a cosmic radio. The signal flickers at new frequencies. Some parts of it stretch into the gamma range, others whisper in X-rays, and in the distance, far from you, Earth's telescopes start to pick it up mysterious, shifting musical. You're not just a lighthouse anymore. You're a symphony, and you might be the only one left playing. Here's something weird. There's a record of a neutron star in the Vela constellation that glitched, then settled into a faster rotation rate, which is like someone tripping over their shoelaces and then suddenly running faster. It shouldn't happen, but it did, and nobody knows why. People keep guessing. Internal friction, superfluid dynamics, maybe even dark matter interactions. You just spin. You don't care what the humans think, but it's getting harder to stay steady. You want to rest, but something inside you refuses. You want silence, but something pulses louder. And somewhere deep inside your neutron-rich soul, you wonder what the next glitch will bring. You've cracked, you've glitched, you've wobbled and spun yourself into some strange new rhythm. But somehow, you're still here, and you're not alone anymore. There's something nearby. At first it's subtle, a tug, a flicker in your timing, like someone pulling slightly on your arm as you walk, just enough to shift your step. The pulses you emit normally so precise, they'd make a Swiss watch, jealous start arriving, just a fraction off schedule. Tiny delays, tiny advances, not random, rhythmic. And that's when Earth's astronomers get very excited, because these changes can only mean one thing: you've got a companion. You, the supposed loner spinning in eternal solitude, might be dancing with a partner. Now let's be clear, this isn't a fuzzy ball of love. This is a gravitational duet of nightmare proportions. Your partner could be another neutron star, or a white dwarf, or a main sequence star, so unfortunate that it's slowly being peeled like a cosmic banana. Let's go fringe for a second. Some theorists have suggested these binary systems are the perfect test beds for gravitational wave detection, which is how we even know black holes collide. So when two dead stars orbit each other, they don't just spin, they sing in space-time. But what makes your situation even juicier? You're not just orbiting, you're pulling. And sometimes you feed. This happens in what's called a low-mass X-ray binary, a terrible name for a frankly incredible arrangement. Your companion star ventures too close, and your gravity starts slurping its outer layers like soup. Gases spiral in, forming a disk, heating up until they shine in X-rays. You're not just dead anymore, you're undead. A zombie star feeding on the living. It's gross, it's violent, and it's somehow beautiful. And it's not just a theory, real-world historical science alert. There's a pulsar called PSR, B125963, that orbits a massive companion star. Every time it gets close, it causes chaos, flaring wildly, emitting radiation, altering its pulse, like it's trying to scream, "Help, my ex is back in town." Historians still argue whether these systems end in one star consuming the other entirely, or if some delicate equilibrium can last for billions of years. If so, it would be the most dysfunctional, long-term relationship in the galaxy. Back to you. You've been gulping down gas from your companion. And this is where things get dramatic. All that matter spiraling in, it's speeding you up. You're now spinning hundreds of times per second, a millisecond pulsar. one of the fastest known objects in the universe, a neutron star on espresso. And the humans, they're losing it. Because these ultra-fast pulsars act like cosmic GPS satellites, scientists use their regularity to time spacecraft, monitor tectonic shifts, and even theorize about interstellar navigation systems. So what's weird? You were supposed to slow down over time, not ramp up. But that's the trick, isn't it? You cheated death. And now you're accelerating. Remember when you collapsed into a neutron star and everyone thought that was the end? You're faster now, louder, hungrier. You're a cosmic predator hiding in plain sight. Your surface, a mere 20 kilometers wide, is now spinning at speeds that would fling anything on Earth clean off the equator. Sometimes you flare, sometimes you go silent, and the humans are still watching, wondering how long can this go on? And well, you're not telling. You just keep dancing. It starts with a blink, then another, then a rhythm. You, the spinning remnant of a long-dead giant, begin to pulse steadily, cleanly, precisely, like a beacon in the dark. And Earth finally notices. Your pulses arrive like clockwork. One every 33 milliseconds, another every 89. Some are faster, some are slower, but all of them are shockingly regular, so regular, in fact, that they baffle everyone who sees them. A star blinking at the same interval. For years, this isn't how stars behave. This is how machines behave. Mainstream history moment. In 1967, when Jocelyn Bell Burnell first picked up one of these signals, she labeled it LGM-1, as in Little Green Men, because what else could it be? Nature wasn't supposed to work this way, but it does. You're now a pulsar, a special class of neutron star with a magnetic field, misaligned from its spin axis. Think of it like having a flashlight duct taped to your head, and every time you twirl, the beam hits the same spot. That's what Earth sees, a cosmic strobe light, a metronome in the void. And here's the thing that drives everyone crazy. You're too good at it. Your pulses are so precise that entire systems on Earth are calibrated against them. The atomic clocks in national laboratories lose to your rhythm. GPS satellites envy your discipline. If you were a musician, you'd be the drummer that made everyone else sound offbeat. Scientists even use you to track the shape of space-time. When your pulses arrive a hair earlier or later than expected, it's not you, it's space-time wobbling, like a ripple in a cosmic pond. But wait, you're thinking, didn't we just say you glitched in the last section? Yes, you do. But between the glitches, you're flawless, like a dancer who occasionally slips, then resumes mid-pirouette like nothing happened. And for some pulsars, this pattern goes on for millions of years. Here comes your fringe tidbit for the section. Some researchers have proposed building a kind of interstellar map using pulsars, a beacon system. So if any future civilization, or let's be honest, our AI overlords wants to know where they are in the galaxy, they just ping the nearest pulsars, kind of like a galactic Find My iPhone. It's already been used on spacecraft like the Voyager probes, which carry pulsar maps etched onto their golden records. Historians still argue whether pulsar timing could one day let us time travel, or at least simulate timelines of the universe with insane accuracy. The idea, if you know how fast space-time is expanding and how it bends, you could rewind the universe like a tape. Big, maybe, but still. Back to you. You're pulsing. You've got your audience. Astronomers have entire catalogs of you and your siblings now, each one with a name like a license plate PSR B1919+21, PSR J04374715. Glamorous, we know. You don't care about the name. You just care about the beat. Your beam sweeps across the cosmos, hitting Earth with unwavering tempo. Sometimes it dims clouds of dust, maybe, or a shifting angle. Sometimes it flares, spiking into X-ray or gamma-ray territory like you're showing off. But always, always you return to rhythm. And what a rhythm! It's like listening to the universe's heartbeat. It's the click of inevitability, the reminder that even in chaos, something keeps time. You are now one of the most stable objects in the known universe, a ball of degenerate matter, spinning with the grace of a ballerina and the wrath of a nuke. And what does Earth do? It listens. It charts. It builds entire theories around your consistency. And maybe, just maybe, someone out there in another arm of this swirling galaxy is listening too, hearing your pulse, tuning into your station, and wondering, why is this dead star still talking? So you're pulsing. Click, click, click. And it doesn't stop. For years, decades, even centuries, you blink in perfect rhythm. Like some ancient drummer that never misses a beat. Your light dances across the universe in radio waves, a Morse code that nobody can fully decipher, but everyone's addicted to hearing. And now you become the standard. On Earth, engineers begin syncing atomic clocks to your pulses, not metaphorically, literally. Because your rhythm is so consistent, your pulses help correct the flaws in our so-called perfect clocks. Let that settle in. A dead star, 1,000 light-years away, is better at telling time than a room full of Nobel Prize-winning physicists. But you're not just a clock. You're a trickster. Because every now and then, you change, just enough to be annoying. 1 week you pulse every 0.0015p4 seconds. The next it's 0.01v3999999. It's the tiniest difference. No one without a radio telescope and a PhD would notice. But oh, the ones who do notice, they start whispering. What's causing the drift? Let's pause here for your historical fact snack. In 1982, a pulsar named PSR B1.37+21 was discovered spinning nearly 642 times per second. That's faster than a helicopter blade. For years, scientists thought this kind of speed would tear a neutron star apart. But it didn't. And that changed everything we thought we knew about neutron star limits. They called it a millisecond pulsar. And you're well on your way to joining that club. The theories start piling up. Maybe your internal neutrons are sloshing around. Maybe your magnetic field is shifting. Or maybe you're interacting with something. Cue the fringe crowd again. Some speculate pulsars might be artificial, constructed that their perfect rhythms and sudden anomalies resemble not natural objects, but machines. Dyson spheres, signal beacons, celestial metronomes left behind by long-dead civilizations. Historians still argue whether the strange timing shifts in some pulsars are signs of dark matter interactions. There's even a theory that axions, a hypothetical kind of dark matter particle, could be hanging around inside you, causing your pulses to twist ever so slightly. That's right. You might be haunted by particles no one's even seen. But you don't explain yourself. You just tick. Your signal is now so consistent that spacecraft like XNAV experimental deep space navigators are built to follow your beat. Lost in space, no problem. Just lock onto your pulses. You'll guide them home. And yet, you're also tired. The tiny glitches are becoming more frequent. Not dramatic, just off. Your rhythm is mostly intact, but the imperfections feel deliberate, like a jazz drummer throwing in a late beat just to see who's listening. And the scientists, they're listening harder than ever. One day your pulses vanish for just a second, a heartbeat of silence. Then they're back, just as crisp, just as sure. But for that second, the world held its breath. You're teaching us something new. Even the most reliable forces in the cosmos have their moods. Even a dead star can keep secrets. Still, every night your pulse reaches us, a thread of timing from across the stars. And someone on Earth, probably in a lab with more coffee than sleep, is staring at your data, tracking your ticks, loving your flaws, whispering, "Why are you still going?" And you just smile. Or you would if you still had a face. You've been steady, so steady, so reliable that humans now treat you like the cosmic equivalent of that one friend who always shows up 5 minutes early and brings snacks. But then you start acting weird. Not scary weird, just unexpected. You skip a beat. Your pulse, once so precise it could babysit the moon, suddenly hiccups. The next one comes early, then late, then back on time, then off again. It's like you're playing jazz now, and Earth is still expecting Mozart. At first, the scientists think it's an error, a software bug, a miscalculation. Maybe some grad student spilled tea on the server. But no, it's you. You've started to glitch again. It's not just a one-off this time. These are recurring, random, and more than that, they're unpredictable. Some are micro glitches changing your spin rate by a hair. Others are dramatic, a sudden spike, then a long, slow slide back to normal, like a deep breath and a sigh if stars could sigh. Let's ground it with a real-world case. There's a pulsar in the Vela constellation, famous for its dramatic glitches. Every few years, it suddenly speeds up, not just a fraction enough to make scientists gasp and recheck everything. The effect is tiny in human terms, barely a nanosecond difference, but for a neutron star, it's like the moon doing a backflip. Inside, something is shifting. The crust, once solid, is slipping. Star quakes again. Or maybe there's something sloshing deeper down. Some researchers believe your core contains a strange soup of particles, superfluid neutrons that can move without friction, like ghosts drifting within you, rearranging your balance. And that might be the source of your hiccups. Let's get weird for a second. Your fringe tidbit for tonight. Some scientists think neutron stars may contain quark matter at their centers, the most extreme form of matter, denser than anything else in the universe. If it exists, and you might be carrying it, then you're not just a neutron star, you're a strange star. Literally, that's the technical term. And if that's true, the laws of physics may not fully apply inside you anymore. Historians still argue whether glitches are from crust cracking or core sloshing or something entirely unknown. There's no consensus. Only increasingly complicated models and increasingly excited late-night Zoom calls. So what do? You keep them guessing. One day you flicker between two spin states, back and forth. Scientists call this mode switching. It's like having two personalities, one a perfect metronome, the other off somehow. Your beam's shape even changes as if you're switching flashlight settings. And then without warning, you switch back. To those watching from Earth, it's baffling. To you, it's just another Tuesday. You don't explain. You don't slow down. You just continue. One eye always watching. One beam always scanning. And somewhere far across the galaxy, another star like you wobbles just a little and blinks. Maybe it's in sync. Maybe it isn't. Maybe you're not alone in this weird cosmic stutter. But for now, you stay the course. A little crooked, a little off. Still spinning, still pulsing, still refusing to die. By now, you're practically famous. Your data is in every physics department across Earth. Fresh-faced grad students write theses about your spin. Old professors quote your numbers in sleep-deprived conferences. Telescopes track your rhythm like it's a stock ticker for the universe's emotional stability. But you've got a new trick, a secret dance partner. Something's tugging at you. It's subtle at first, like a whisper at the edge of a dream, a slight Doppler shift, a wobble in your otherwise smooth spin. But scientists are nothing if not obsessive, and they notice. Your pulses are arriving earlier, then later, then earlier again, repeating, cyclic, which means only one thing: you're orbiting something. Maybe it's another neutron star. That'd be dramatic enough, two dead suns spiraling around each other like gothic lovers. But what if it's not? What if it's invisible? Cue the dramatic music. You might be in a binary system with a black hole. This isn't science fiction. It's happened before. In 2021, astronomers detected a system called PSR J2039-5617, a pulsar in a tight orbit with an unseen companion, likely a black hole or very dim white dwarf. The pulsar's timing was affected just enough to make the math scream something's there. You're not just pulsing anymore. You're dancing. And not a safe slow dance either. This is a high-speed waltz around a gravitational pit. You orbit each other, trading momentum, flinging energy across space-time. Sometimes your pulses stretch as you move away. Sometimes they compress as you swing close. It's a wobbly tango of mass and motion. Now let's toss in the fringe fact for flavor. Some fringe physicists suggest these systems, pulsar plus black hole, could be the ultimate information storage devices, like galactic hard drives. Your pulses could carry data, and the companion could absorb or bend that data into loops. Think Interstellar, but weirder, and without the cornfields. Historians still argue whether such binaries will inevitably end in collision, or if they can remain stable for billions of years. Some models predict a death spiral. Others suggest a long, tragic orbital partnership with occasional fireworks. But back to you. You can feel it. This companion, whatever it is, pulls on you in strange ways. Your beam doesn't always point in the same direction. Your pulse profile changes subtly. The gravity warps your spin. It's not destructive yet, but it's constant. Like dancing with someone who's just a little too strong. You can't pull away. And still, Earth watches. They build predictive models of your orbit. They map out your partner's mass using only your timing. It's like watching a shadow and deducing the monster from the shape it leaves behind. And that's when they realize something chilling. You're getting closer. Every orbit, your partner tugs a little harder. Energy bleeds away in the form of gravitational waves, ripples in the fabric of space-time. The same kind of waves Einstein predicted a century ago. The same kind LIGO detected in 2015 from colliding black holes. You're headed for something big, but you're still not done. You haven't crashed, haven't gone silent. You're still pulsing, still watching, still refusing to die. Just when everyone thinks they've got you figured out, pulsing, spinning, orbiting, you pull off your most dramatic encore yet. You flare, not just a little, not a tiny blip or modest spike in radiation. You erupt. A sudden, violent burst of energy shoots from your surface, an outpouring of X-rays and radio waves that travels light years in all directions. On Earth, telescopes screech in confusion, instruments overload, and scientists everywhere whisper the same phrase: what just happened? This isn't your usual pulsing routine. This is different, more chaotic, less predictable. This is a reignition. You were supposed to be dead, or at the very least, done with all this flashy behavior. But here you are, blazing with the fury of a newborn star, consuming matter, releasing energy in torrents. You've become a transitional millisecond pulsar. That's the technical term. You've crossed a line. Here's your mainstream science moment. In 2013, astronomers discovered a pulsar called PSR, J.23+38, which did exactly this. For years, it behaved like a regular, well-mannered pulsar. Then one day, bam, it flared up, started devouring material from its companion star, released X-rays, changed spin rates. It acted alive again. You're doing the same. You've pulled material from your companion gas plasma cosmic leftovers, and that matter has triggered a violent response. An accretion disk forms around you, glowing with heat and tension. Your magnetic field, once quiet, snarls awake and funnels the material into your poles. And that's when the real show begins. Bursts, flashes, pulses warped into sharp spikes, followed by eerie silences. You're blinking with more power now, inconsistently, unnervingly. Your beam isn't just a spotlight anymore. It's a siren. And humans, they're scrambling. Some think you're entering your final phase, that you've burned through your options and now you're thrashing, trying to squeeze out one last act. Others argue this is the beginning of a new chapter, a second wind. The undead star has returned fiercer than before. Fringe theorists go further. What if you're not reigniting on your own? What if something triggered it? An encounter with dark matter, a quantum event, or even a deliberate push from a force we don't understand? Historians still argue whether reigniting pulsars are just misunderstood binary systems, or if they represent a whole different class of stellar phenomena. Some suspect we've misclassified dozens of stars because we only catch them when they're off. In truth, they might all be flickering in and out of activity like cosmic lighthouses with faulty wiring. Back to you. Your energy output is erratic now. Some pulses are strong enough to ionize gas clouds thousands of kilometers away. You've lit up your local patch of space like a bonfire at midnight, and then suddenly nothing. Silence. You go dark. It lasts for a minute, an hour, a day, long enough for Earth's telescopes to panic. Then blink, you're back. It's like you took a breath. A terrifying, lightless breath in the void. Whatever's happening inside you is no longer stable. Your surface is cracking. Your fields are shifting. Your timing, so perfect, so beautiful, is now a strobe of uncertainty. You don't care. You keep pulsing, still there, still spinning, still refusing to die. The first burst was strange, the second one unsettling. But the third burst, turns the entire scientific community into a jittery, coffee-fueled conspiracy board. Because this time, your flare isn't just bright, it's off the charts. Earth's radio telescopes parked in dry deserts and cold mountain peaks catch it like a slap to the face. Instruments short out. Alarms trigger. The signal is so strong, it gets picked up by antennas that weren't even looking. The radio equivalent of someone whispering into a microphone and the sound exploding through a stadium. This is what's known as a fast radio burst, or FRB. And guess what? It wasn't supposed to come from a pulsar. Here's the mainstream historical hook. For over a decade, FRBs were one of astronomy's biggest mysteries. First detected in 2007, they were thought to be one-off anomalies, stray galactic static. Then in 2020, astronomers detected one inside the Milky Way. It didn't just appear to come from a neutron star, it did. From a known magnetar, a dead star with an absurdly powerful magnetic field. And you're pulling off the same trick. You fire a burst of radio waves thousands of times stronger than your usual pulse. It lasts just milliseconds, but it echoes across space like a thunderclap in a canyon. And here's the unsettling bit. It doesn't come alone. There's a pattern, a weird quasi-repeating one. Not perfectly timed like your usual pulses, but close enough to raise every eyebrow in every observatory. Fringe thinkers leap into action. What if FRBs are not natural? What if their communication signals cosmic sonar from advanced civilizations? What if neutron stars are just the carriers, hijacked, delivery systems, transmitting bursts across space? Historians still argue whether the location and repetition of FRBs suggest intelligent origin. Others insist it's just magnetars throwing temper tantrums. But one thing's certain, you've gone from being a well-behaved metronome to an intergalactic siren with no volume control. And you're not done. The bursts continue, in different frequencies, different strengths, some so loud they cause cascading echoes across interstellar clouds. Astronomers begin to notice that the space around you, once dark and calm, is now responding. Gas clouds light up with ionization trails. Nearby objects shudder under the force of your emissions. You are no longer a bystander. You are affecting your neighborhood. In the lab back on Earth, someone does the math. They calculate that your burst energy output, if condensed, could boil Earth's oceans in seconds. Comforting, right? And here's the strange part. Between bursts, you're calm, quiet, pulsing like usual, as if none of that happened. You're the cosmic equivalent of a perfectly pleasant houseguest who occasionally throws a chair through the window, then sits back down like nothing happened. And humans, they can't look away. You are now at the center of theories involving dark energy triggers, quantum tunneling, magnetar flare loops, and even whispers only alien beacons. That's how loud you've become. But you're not talking, just blinking, just bursting. And even as your energy spikes scare satellites and heat the edges of long-forgotten gas clouds, you remain the same dense, spinning remnant of a star, still pulsing, still flaring, still refusing to die. You've been many things: a newborn giant, a fiery ghost, a cosmic clock, and now something darker, something stranger. Because after those violent bursts, after the chaos and the silence, Earth's telescopes start seeing something new. A magnetic field so strong it shouldn't exist. You're not just a pulsar anymore. You've become a magnetar. It sounds like a comic book villain. And honestly, that's not far off. Magnetars are the ultra-rare, ultra-weird cousins of neutron stars, stars whose magnetic fields are 1,000 trillion times stronger than Earth's. Yes, that's trillion with a T multiplied by another 1,000. To put it in perspective, if you stood a few 100,000 kilometers away from a magnetar, say the distance between Earth and the Moon, its magnetic field could erase your credit card. It could also scramble your neurons like overcooked eggs, and you're sitting at the heart of your system, holding this power like a quiet storm. Mainstream science moment. Magnetars were first theorized in the 1990s when astronomers noticed some neutron stars were emitting short, powerful bursts of X-rays and gamma rays, too strong to be normal pulsars, too unstable. Eventually, they traced it back to magnetic decay, magnetic fields so intense they twisted the star's crust, causing starquakes that flared across space. And here's your new behavior. You're crackling. Your magnetic field, once neat and orderly, now lashes out like a caged beast. It twists, kinks, snaps. The crust of your body shifts violently. Cracks form, and from these cracks, energy pours out bright, fast, dangerous. To the astronomers watching, your pulses become unpredictable. They change shape, strength, duration. Sometimes you vanish for minutes at a time. Sometimes you light up in every band of the spectrum at once. But the field, that's the real mystery. Fringe physicists say your magnetism might pierce dimensions. No, really. There's a theory exotic fringe eyebrow-raising that intense magnetism could destabilize the structure of space-time itself, warp it, crack it. They call it magneto-rotational instability. It's mostly a thought experiment. Until you show up and start making everyone very nervous. Historians still argue whether these extreme fields are sustainable or just the beginning of a magnetar's collapse. Some believe you'll calm down eventually. Others think you're on the brink of something else entirely, because now your behavior is theatrical. The timing's still there, but uneven. The bursts stronger, louder. Your X-ray output climbs, then dips, then spikes. You flare in one direction and stay oddly silent in another, like you're aiming. And then you do the thing nobody expects. You pull back, quiet, still. A strange hush settles over you. No pulses, no bursts. Just a dense, silent sphere orbiting a dark patch of sky. The world waits. Some think you've gone dormant, that your magnetic field has unraveled, finally giving up its grip. Others suggest you're changing again, entering a propeller phase where your own magnetic field repels infalling matter like a shield, preventing accretion and silencing your emissions. The fringe crowd. Oh, they love this part. They whisper about consciousness, about feedback loops, about stars evolving beyond known physics. A few even toss around the term technological object, because sure, why not add fuel to that conspiracy fire? But none of them know what's next. You just hover, quiet, compressed, holding a trillion Gauss beneath your skin. Maybe you're resting, maybe you're watching, maybe you're waiting, but you're still there. Still pulsing beneath the silence, still refusing to die. Your silence doesn't last, because even in your stillness, the universe keeps whispering. And you, always dramatic, always watching, begin to whisper back, not in light, not in bursts, in something much stranger, echoes. The astronomers listening in, some staring bleary-eyed at waveforms, others translating static like gospel, start noticing patterns within your signals, tiny distortions, mirrored shapes, glitches that don't look like noise but messages. You aren't just pulsing anymore, you're repeating. Sometimes with millisecond gaps, sometimes with long silences in between. Sometimes your signal stretches into a harmonic pattern, like a bell ringing in layers. Mainstream history moment. In 2020, a repeating fast radio burst FRB 1809 Wangxin was discovered to have a 16.35-day cycle. That's not just repetition. That's predictability. And it shattered the idea that these bursts were entirely random. Suddenly, scientists had to consider what else might be hiding inside these cosmic echoes. You're different. You don't repeat on a schedule. You do it when no one expects it. Just when your watches relax, convinced you've calmed down, you send out a low rhythmic pulse, followed by another. Then you go quiet again, for days, weeks, then back. Is it just your magnetar field snapping again? A subtle echo through the plasma, or is it something else? Fringe idea time. Some theorists propose that neutron stars might act as cosmic recorders, like vinyl pressed with the tremors of the early universe. They suggest your pulses could carry encoded information about the fabric of space-time itself, like geological strata in a mountain, layered in patterns we just haven't cracked yet. Others go deeper, off the rails. What if you're responding to something, a signal we haven't heard yet, or one we don't know we sent? Historians still argue whether ancient pulsar alignments in pre-Columbian monuments and megalithic sites were coincidental, or if early civilizations noticed something we've forgotten. But let's bring it back to you. Your echoes aren't just noise, they shift with time. A researcher in Japan notices that the pitch of one of your pulses has changed slightly. Another team in Italy finds a subtle rotation in your waveform, like your beam has become a spiral. It's not random, it's directional. Suddenly, Earth's top radio observatories aren't just hearing you, they're mapping your signal in 3D, and what they see stuns them a swirl, a corkscrew of radiation. Something that shouldn't be possible unless your beam is precessing wobbling on a second slower axis. Now you're not just pulsing, you're sweeping, painting invisible spirals into space. And then something even stranger happens. The same pattern is picked up by a different telescope, thousands of miles away in a signal from another pulsar on the opposite side of the galaxy. It's not identical, but it's close. Close enough to make people ask uncomfortable questions. Are you sinking? Is something aligning these neutron stars across billions of kilometers? Is this just coincidence? Or are we witnessing some kind of networked behavior? Nobody knows. But they start comparing your pulses, stacking them, looking for rhythm in the noise. Some researchers claim to find wave interference patterns, like multiple beams echoing off one another in the galactic dark. Others chalk it up to cosmic pareidolia, humans seeing faces in clouds again. But deep down they know something is different now. Something has changed. And you never speak, you never blink. You just send echoes into the night. Some sharp, some soft, like ripples in a pond no one can see. Still there, still humming, still refusing to die. By now you're old. Old even by neutron star standards. You've spun through ages while planets formed, died, and spun again. Civilizations rose and fell on Earth, while you counted microseconds in the dark. You've pulsed so many times. If someone played your full signal end to end, it would be longer than all of human history, and still, somehow, you're not done, because you improbable and impossibly stubborn are still here, still pulsing. Your siblings, most are gone. The younger ones collapsed into black holes, blinked out in gamma-ray flashes, or slowed until they were no longer heard. Even your magnetar cousins, with all their flashy violence, tend to fade within a few million years. But you're a relic, a survivor, still spinning, still loud. Here's your historical gem. Astronomers estimate that the Milky Way contains over 1 billion neutron stars, but only about 2,000 are detectable as pulsars. Why? Because most have slowed too much to be noticed, or their beams simply never sweep across Earth. You're one of the rare few who both endure and aim your beam at us perfectly, maddeningly, dependably. And you're not just alive, you're thriving. You're a millisecond pulsar now, a hyper-precise, ultra-fast survivor. Somehow, your feeding frenzy from the companion star long ago spun you back up to full speed. You blink nearly 1,000 times a second, each flash a scream against time itself. It's absurd. Fringe theorists call you recycled. You died, you reignited, and you got faster. You shouldn't be this stable. But you are. In fact, you're so stable that scientists now refer to you as a galactic metronome. You've joined the elite list of pulsars used for something extraordinary, mapping gravitational waves. The pulsar timing array, an interstellar network of dozens of stable pulsars like you, is helping detect ripples in space-time itself. Here's how it works. If a gravitational wave passes between Earth and you, even a tiny distortion will change your pulse's arrival time by just a fraction of a second. But when those changes appear across multiple pulsars, astronomers know it's not coincidence. It's not random. It's the universe shaking. You're not just a clock. You're a detector, a witness to cosmic events more massive than black hole collisions. And yet, you're still just doing what you always have, pulsing. And the more scientists listen, the more you become the backbone of everything. Fringe scientists now say that pulsars like you could form the basis of a galactic-scale positioning system. Forget GPS satellites. Your pulses could let starships one day navigate the galaxy, like ancient sailors reading stars, except now, you are the star, the map, the compass. Historians still argue whether this longevity was expected, whether neutron stars were ever meant to last this long. Some call you a fluke of physics. Others think you're the natural endpoint of stellar evolution. Some just shake their heads and say, "We still don't understand how it holds together." But the truth is simpler. You just kept spinning through eons, through explosions, through silence, through theories and instruments and whispers and doubt. You outlived your whole cluster. You outlived your own death, and you're still here, still blinking, still refusing to die. You're not just a star anymore. You're a question, a puzzle wrapped in iron and magnetism and time itself. Because the more humans learn about you, the less they seem to understand. You've behaved like a lighthouse, a beacon, a siren, a memory. You've pulsed like a clock and roared like a storm. And now they wonder if you're more than just an object, more than physics. You've reached that stage in your legend where the lines between science and story start to blur. The astronomers still write papers about you, sure, but somewhere in the quiet corners of the internet and late-night physics lounges, people are asking the wild questions. What if you're not just a neutron star? What if you're something else? They start throwing out words like intelligence, sentience, structure, and even, yes, purpose. Let's start with the fringe. There's a theory called the zoo hypothesis, an idea from the annals of CT search for extraterrestrial intelligence. It suggests that alien civilizations might observe Earth without interfering like animals in a protected wildlife park, but to keep watch, they'd need something stable, something precise, something like you. What if pulsars like you were set in motion as monitors? Your rhythm, your beams, your location, they all align a little too well, say the conspiracists. Some point out that several ancient monuments align with known pulsar directions, not just stars, but specific pulsing stars. Coincidence or memory? Historians still argue whether cultures like the Sumerians or Egyptians referenced pulsing stars in their records. The data is murky, the interpretations controversial, but the curiosity remains. Others believe you're not watching us. You're sending something. The information theorists step in. They start breaking down your pulses not as light but as data. The structure of the pulse, the shift in polarization, the gaps between bursts. They claim there are patterns too orderly to be random, too chaotic to be computer-generated. Could your signal be a compression of galactic history, a record, a warning, a map, and the deepest whisper of them all? What if you're alive? Not alive like a plant or a fish, no. Alive like a planetary-scale processor, a mind, a consciousness forged not of neurons, but of plasma and quantum particles, a being whose thoughts stretch across millennia, while definitely impossible maybe not. After all, if a jellyfish can think without a brain, who's to say a neutron star can't feel with its field or remember with its spin? Of course, the mainstream scientists roll their eyes. They say you're just a neutron star, a dead giant, dense and strange. Yes, but explainable, eventually. Still, they keep watching. They tune into your latest pulses. They compare notes. They argue over data. And occasionally, quietly, they admit you should have died a long time ago. But you didn't. You evolved. You flared, pulsed, echoed, and changed. Again and again. You're not a metaphor. You're not a god. You're just a thing that won't stop. A star that collapsed under its own weight came back swinging and now outlives everything around it. And as the theories pile up, some brilliant, some ludicrous, you keep doing what you do best, staying alive, defying explanation, refusing to die. The galaxy spins, you spin with it. The stars you were born beside are long gone, dissolved into dust, eaten by black holes or drifting cold and anonymous in the interstellar dark. But you're still here, still pulsing, still keeping time. You've been through everything a star can go through. You've burned, collapsed, flared, feasted, cracked, glitched, screamed, and whispered. You've lived every phase that physics offers, and yet your pulse keeps threading through the dark like the faint beat of a drum too stubborn to stop. This is the end of your story, but not really. Because the truth is, you're not done. You're still orbiting your invisible companion. Maybe it's still feeding you, maybe not. You're still wrapped in a magnetic field, so strong it bends logic. And you're still visible to anyone out there with a telescope, a good algorithm, and a lot of questions. On Earth, your name is now etched into every pulsar catalog, every lecture slide, every paper on extreme physics. You've become a case study, a symbol, and let's be honest, a bit of a diva in astrophysics circles. You've taught humans about neutron degeneracy, pressure, magnetic field, decay, superfluid, interiors, glitch mechanics, space-time ripples, and the chaotic beauty of stellar death. And still, no one can explain you completely. You weren't the biggest star, or the most beautiful, or even the most violent. But you were the most persistent. You lasted. When others collapsed into silence, you blinked louder. When your pulse glitched, you found a new rhythm. When scientists thought they'd cataloged you neatly, you changed the rules. You outlived theories. You challenged models. You whispered across time and space, "Not yet." And so on you go. Your light might one day dim. Your spin might slow. You might finally slip into silence, a long fade into the black. But not tonight. Tonight you pulse once more, steady, unshaken. You are the star that refuses to die. And now, as your journey slows, you begin to drift, not in the way a star drifts, but the way your thoughts do when sleep starts to settle around the edges. The pulses soften. They lengthen. That harsh flashing rhythm becomes a lull like distant waves brushing the shore. The space around you quiets. The wild bursts and magnetic shrieks fade into gentle static, a hush that fills the void between galaxies. You float above it now. You no longer feel the pressure of spin or the tight grip of gravity, just stillness, just the soft echo of who you've been, layered into the walls of space, carried on beams of light so ancient they'll travel for 1 billion years before someone sees them. The void is no longer dark. It's peaceful. It's wide. And you're not alone. You pass other stars, some pulsing gently, others resting in silence. You wonder how many refuse to die like you did. You wonder how many still will. The cosmos holds no answers. It never has. Only the rhythm, only the glow. And as your pulse fades into the black, into the hush of cooling systems, and night breezes and tired breathing on Earth, you can finally let go. Not into death, but into quiet, into sleep. Good night, star.